Hello everyone. Today in this video lecture we are going to start a new topic, that is the states of matter. Before starting with the states of matter, we have gone through the chemical bonding in detail. There we have discussed different types of chemical bonding present in given molecules. So before starting with this states of matter, we are going to focus on different types of intermolecular attractions found between the molecules in different physical states of the substance. So the heading is intermolecular attractive force operational in molecules. Intermolecular attractive forces. So this intermolecular attractive force is of different types. We have London or dispersion force, then we have hydrogen bond, then we have van der Waals force, so the word van der Waals force is used for all types of weak intermolecular attractive force that is present in the given molecules. So van der Waals force is a common term which is used for all weak intermolecular attractive force present in given molecules. Now look at this London dispersion force is the one of the weakest intermolecular force present in given molecules. So London dispersion force is the weakest attractive force present in molecules. Now this London or dispersion force is also what we call as induced dipole type. Induced dipole type. And this induced dipole type is operational in non-polar molecules. Observed in non-polar molecules. So any type of intermolecular attractive force operational in non-polar molecule is known as induced dipole, which is the weakest of all intermolecular attractive force, commonly known as London or dispersion force. So look at this, we are using a particular term, induced dipole. Molecule is non-polar, but in presence of another molecule, a temporary dipole is induced for a given moment. Because of this temporary induction of dipole, an attractive force occurs which is known as induced dipole type. So suppose look at this, we have a molecule Suppose we have a molecule, non-polar molecules, like we can look at this. We have hydrogen molecule, we have helium molecule, we have nitrogen molecule. These are all non-polar molecules. So whenever we have this non-polar molecule, the attractive force is induced dipole, induced dipole. So now look at this, let's take this. We have one non-polar molecule. This is second non-polar molecule. They are at very far distance, so there is no polarization of this molecule. Now look at this. This is the nucleus, this is the nucleus. Now when these non-polar molecules are brought closer to each other, this nucleus will repel this nucleus, whereas this nucleus will attract the electrons of this non-polar molecule. So when they are brought together, this molecule will temporarily induce a dipole in this molecule. Similarly, this molecule will also induce a temporary dipole here. That means this nucleus will repel this nucleus. Simultaneously, this nucleus will attract the electrons of another molecule. So this is what they call as temporary induction of dipole. So look at this. So this nucleus and nucleus will repelling each other. This similarly, this nucleus repels this nucleus, whereas this attracts the electron. So we have this. So therefore look at this. Nucleus repulsion, electron nucleus attraction. So because of this, there is an attractive force. This attractive force is known as induced dipole, induced dipole. Induced dipole, this is induced dipole. So induced dipole type interaction is known as London dispersion force, which is the weakest. So keep in mind, this is found in non-polar molecules. So whether the molecule is a polar or non-polar, even the molecule is a non-polar, then in presence of another non-polar molecule, there is induction of a temporary moment, or dipole is momentarily introduced, and at that moment there is a temporary attractive force between them. This is known as London dispersion force. Now we are not going to detail the hydrogen bond. This hydrogen bond is dipole interaction of specific type involving hydrogen, which is covalently bonded to an electronegative atoms like nitrogen, fluorine, oxygen, and this hydrogen is sandwiched between two electronegative atoms. So this hydrogen is also a van der Waals force, but specific involving hydrogen, so we are having a separate name. So this is of two types, intermolecular, intramolecular, we have discussed earlier, so we are not going into details of hydrogen bond. Then van der Waals force. This van der Waals force, we say this is dipole type interaction. So this is normally found in polar molecules. So these polar molecules means molecule itself possesses polarity. So whenever we have polarity in the molecule, then between opposite charges there is an attractive force, which is known as dipole type interaction. Take this example. We have HCl molecule. So look at this hydrogen Cl bond. Chlorine is more electronegative, so this is negatively polarized. Hydrogen less electronegative, this is positively polarized. So we have this HCl. Suppose we have this HCl. This is HCl. So this is hydrogen, the positively polarized, this is negatively polarized, Cl minus. Similarly, another HCl molecule, this is HCl molecule, so this is positively polarized, this is negatively polarized. So between these two, there is attractive force. This attractive force between the polarized molecule is known as dipole-dipole type. So means molecule should be polar, and in this dipole, opposite charges will undergo some attractive force, intermolecular attractive force. That is what we call as dipole-dipole type. So that is polar molecules may possible. Another is dipole induced dipole. Dipole induced dipole type. So dipole induced dipole type, this is found between molecules which are polar and another molecule which is non-polar. So between polar and non-polar molecules, that means one of the molecules should be polar molecule, other molecule should be non-polar. So these non-polar molecule will introduce a temporary dipole to the non-polar molecule, similar in the same fashion. So in absence of this polar molecule, this non-polar molecule is not polarized. But in presence of this polar molecule, this is temporary, and non-polar molecule is a temporary polarity is introduced, and in between these two there is an attractive force which is known as dipole induced dipole type. So take this example. So we have HCl plus suppose we have this. Take this H2. So now look at this. This is HCl. This is hydrogen. This is polar molecule. This is non-polar molecule. So if you look at this. This is HCl, so this is partially positive polarized, this is negatively polarized. We have, look at this is hydrogen, this is non-polarized. Now look at this is negative. So these negative will repel the electrons of this non-polar molecule, whereas this negative polarity of HCl will attract the nucleus of this H2 molecule. So between these two, a polarity is temporarily introduced. So because of this, again there is attractive force between these two. We say this is dipole induced dipole type. So polar molecule will introduce a temporary dipole in the non-polar molecule, and in that time an attractive force between the opposite ends of the dipole takes place, which is known as dipole induced dipole. So in any given molecule we can have this type. If the molecule is a non-polar, we have a specific type, that is induced dipole. Induced dipole, London dispersion force, which is the weakest. If the molecule contains hydrogen which is attached to an electronegative atom like fluorine, nitrogen, oxygen, then we have a special type of bond that is known as hydrogen bond, which is nothing but dipole type. Then we have a van der Waals force, that is dipole type, which is formed between the polar molecules. We have taken example. Then if the molecule is between polar and non-polar, then we have dipole induced dipole type interaction. So this is some of the intermolecular attractive force, which is not actually a chemical bond but an attractive force present in any given molecules. So all this weak intermolecular attractive force operational in compounds is given a specific name, that is van der Waals force, in honor of the scientist van der Waals force, van der Waals, who discovered this intermolecular attractive force to explain the behavior of gases. So after learning this, intermolecular attractive force. Now we are coming back to the main chapter, that is the gaseous state. So we are starting with states of matter. Gaseous state. Now here I am going to discuss the important properties of gas. We all know the difference between solid, liquid and gas based on the distance between the particles as well as the attractive force between the constituent of the particle. If the distance between the particle is very close to each other or the attractive force is very strong, then we say that is solid state. If the distance between the particle is very large or the attractive force is the minimum, then we say that is gas. In between these two we have a liquid. So we are going to focus on this gaseous state. Gaseous state, the intermolecular attractive force is the weakest. Distance between the particle is the maximum. They have property of diffusion, that is intermixing of gas. They can be easily compressed. They take the shape of container in which means they occupy the whole volume. The total volume of the gas is the volume of container. They do not have a specific volume. So these are some of the properties of gases. Apart from this, there are some laws which governs this gaseous state of matter. So we are going to focus on that. So first is experimental gas laws. Experimental gas laws. Under this we will discuss Boyle's law, we have Charles' law, we have Gay-Lussac's law, we have Avogadro's law. So these are the four gas laws we are going to discuss in detail. What is their statement, what is the mathematical relationship, and its application. So coming to the first, that is the Boyle's law. So these are observed experimentally, and these experimental gas laws के बाद we are going to develop a theory which is going to explain this experimental gas laws. So now coming to the first, that is Boyle's law. So starting with Boyle's law. So first, whenever we discuss Boyle's law, the first thing that we have to keep in mind is temperature of the gas should remain constant. So temperature is held constant. Similarly, the quantity of gas, that is mass or amount, number of mole, N for number of moles, so number of moles is again held constant. So if number of moles is constant, that means the mass of gas is remaining constant. So these two should be remaining constant. If temperature is not constant or number of moles is not constant, then Boyle's law will not be applicable. So for Boyle's law to be applicable, temperature and the number of moles should remain constant. So as far as statement of this Boyle's law is concerned, for a given mass, that is for a mass with for a gas with fixed number of moles or fixed mass, the volume occupied by the gas is inversely related to the pressure at constant temperature. Simply we saying pressure exerted by the gas is inversely proportional to the volume occupied by the gas at constant temperature and amount of the substance, or at constant temperature for a fixed mass of gas, pressure exerted by the gas is that inversely proportional to the volume occupied by the gas. So pressure exerted by the gas is inversely related to the volume occupied by the gas at constant temperature and amount of mass, or at constant temperature and for a fixed mass of gas. In some of the books will find the fixed mass, in some of the books will find fixed quantity, so both are remaining same. If mass is fixed, quantity, that is amount of substance, is fixed. So I repeat the sentence again. For a fixed mass of gas at constant temperature, pressure exerted by the gas is inversely related to the volume occupied by the gas, where P is the pressure, V is the volume occupied by the gas. So therefore look at it, this is the main equation. So we have this main equation. So now look at this. This can also be written as pressure is equals to some constant K divided by V. So where K is a constant of proportionality. So let's say this is equation 1. The same equation can also be written as pressure into volume is always constant. So if pressure into volume is constant, that means temperature and amount of substance remaining constant. If this is the case, then P1 V1 will always be equals to P2 V2, which is always a constant. That means pressure volume. Suppose we increase the pressure, then correspondingly volume will decrease. Then another pressure, then volume. This product of pressure and volume is always a constant term. So let this be equation number 3. Now look at this. The same equation can also be written in terms of logarithmic form. Now we take the logarithm of equation 1, we get logarithm of pressure P is equals to logarithm of K minus logarithm of, we say, plus logarithm of 1 by V. So take this basics of logarithm. Log A into B is equals to log A plus logarithm of B. Log A by B is equals to log of A minus log of B. Log A raised to the power B is equals to B times log A. These are some of the basics of log. So look at this. This is log K minus log V. That is the equation number 4. So these are the various forms of Boyle's law. That means if pressure is high, volume will be low. If pressure is low, then volume will be high. Pressure and volume is always inversely related at constant temperature and fixed mass of gas or number of moles of gas remaining constant. So these are different forms of same law, that is Boyle's law. So this is logarithm form, this is pressure volume at different temperatures, pressure and volume product is always constant, pressure versus volume. Now we have to explain all these equation in graphical form. Before this, let me take up what is the meaning of this pressure into volume. So look at this. This dimension of pressure into volume. Pressure into volume. We define this pressure. Pressure is force per unit area. This is force. So force per unit area, this is defined as the pressure, and volume is area into length, that is defined as volume. So therefore pressure into volume is equals to force per unit area into length. So we have force into distance. So force into distance, this is defined as work done. So work done is nothing but energy. So that means the dimension of pressure into volume is equals to the dimension of energy. So pressure into volume of a gas signifies the energy content of gas. So energy is measured in terms of joule. If for a larger quantity we define in terms of kilojoule. So simply saying the dimension of pressure into volume is always equals to energy of the gas. So pressure into volume defines the energy content of the gas. So this thing we have to keep in mind. So look at this. These Boyle's law, different equations have been given. So these equations represents the same gas law, that is known as Boyle's law. So let's do the graph of these different equations. So graphical representation. Graphical representation of Boyle's law. Now in this Boyle's law, temperature remaining constant. So during this process, temperature of the gas has to remain constant. So temperature constant, a process in which temperature remaining constant is known as isothermal process. So the graphs representing Boyle's law are known as isotherms. So here temperature is a constant. So the graph is known as isotherms. So isotherms of Boyle's law. So graph representing Boyle's law is known as isotherm because of temperature being constant. So we have looked at these different equations. So let's take up different equations. So we have this pressure and volume. Now, as I told you, pressure and volumes are inversely related. So this pressure volume graph looks like this. So if volume is increased, pressure is decreased. So this is at a given temperature. If the graph is at different temperatures, graphs looks like same. So suppose this is at temperature T1, this is at temperature T2, this is at temperature T3, this is at temperature T4. So if someone asks to compare the temperature T1, T2, T3, T4, so moving from T1 to T4, temperature will increase. That means T4 is greater than T3, which is greater than T2, greater than T1. This is at low temperature graph, this is at high temperature gas. for the same gas at different temperatures. So this is equation 1, the graph of equation 1. This represents equation 1. The same equation 1 can also be represented in this way. Instead of V, I am going here 1 by V. Pressure versus 1 by V. So if you look at this equation represents an equation of straight line with constant C. C, that is 0. This K represents the slope of the graph. So this is equation of straight line passing through 0. So if 1 by V is 0, pressure is equal to 0. If 1 by V increases, pressure increases by K times that value. So we say this graph is an equation of straight line passing through origin. So we have this. Suppose if the graph is for different temperatures, all graph will pass through origin. So this is a temperature T1, T2, T3, T4. So again temperature increases from T1 to T4. So this again represents equation 1. Now let's go to this graph, equation number 2. We have looked at this pressure into volume. This pressure into volume. So we have pressure into volume versus pressure or volume. So for any given pressure or for any given volume, the product pressure into volume is always a constant. So since the product of pressure into volume is always a constant, we say this graph remains constant whether you increase the pressure or increase the volume. The graph will always remain constant. Similarly for different for different temperatures, the graph can be written as, so this is T1, T2, T3, T4. Again moving from T1 to T4, temperature increases. So this represents equation 2, the graph of equation 2 and 3. P into V is always a constant. P1 V1 equals to P2 V2 is always a constant. So this equation 2 and equation 3. Now coming to equation number 4. Let's make a graph between logarithm of P and the logarithm of 1 by V. Logarithm of P versus logarithm of 1 by V. Now if you look at this equation is an equation of straight line, the slope being 1 and intercept is positive. So we have look at this, slope is positive. So graph will have slope positive. And if you extrapolate, this meets at 0 value and this value, this equals to log log K. This is the intercept and the slope. This is slope. The slope of the graph is 1. This is equation 4. Another form of equation form that we can observe is log P versus log V. If we have a graph for log P and log V, the slope is negative. So we'll have this graph. Log P versus log V. Here the slope is negative So we have a decreasing slope. Extrapolation, this value, that is log k, and this is slope. So the slope of the graph is minus 1. So both these graph represents equation 4. So this is different graphical representation of same gas law, that is Boyle's law. So Boyle's law is same. Main statement is pressure and volumes are inversely related provided temperature and number of moles or the quantity of gas remaining constant. So the same statement can be given in different, but can be represented in different ways. Based on this, we can develop different types of graphical representation. All this graphical representation explains Boyle's law. So if sometimes the question says which of the following graph represents Boyle's law, then we have to give this. For this equation 1 graph, the slope of the graph is equals to k, that is constant. So Boyle's law, temperature and amount of substance remaining constant. Now let me give an example. We are very familiar with playing with balloons. Balloons से हम लोग खेलते हैं. So we have a balloon. Now we inflate this balloon by blowing air. या पंप से या मुंह से इसको एयर भर के हम इसको खेलते हैं. So during the whole process, I am just keeping the temperature constant, that is at room temperature. We are not changing the temperature. Now initially the ball, that is deflated ball, volume is approximately 0. Now we inflate this balloon by blowing air. So during this inflation of balloon, volume of balloon increases. As the volume of balloon increases, the volume of air also increases, that is the case. Simultaneously pressure also increases. So during inflation of balloon, both pressure and volume increases simultaneously, though we are keeping the temperature constant. The question is this the violation of Boyle's law? So the answer is, as I told you, for this Boyle's law to be applicable, both temperature and the amount of gas should remain constant. So in this example that I have just spoken about, inflation of balloon, when both pressure and volume increases simultaneously, even if the temperature remaining constant. So in this process, Boyle's law is not applicable. The reason being, we are increasing or we are changing the amount of gas. Whereas Boyle's law says amount of gas should remain constant. But in this process, we are increasing amount of gas. We are blowing air. So the quantity of air increases. So as the quantity of air changes, Boyle's law will not be applicable. So this is all about Boyle's law. Now coming to next, that is Charles' law. So second is Charles' law. Now for this Charles' law, the condition is pressure of the gas has to remain constant and the amount or mass of gas should also remain constant. So both pressure and the amount or the mass of gas should remain constant. So again look at this. For Charles' law to be applicable, both pressure and amount of gas has to be kept constant. If pressure changes, then Charles' law is not applicable, or if amount of gas changes, then again Charles' law is not applicable. So under this condition, now look at this. The volume occupied by the gas is directly proportional to the absolute temperatures. Now look at this statement very carefully. Don't say the volume is directly proportional to temperature. If I say the volume is directly proportional to the temperature, then this statement comes out to be wrong. Volume occupied by the gas is directly proportional to the absolute temperature, means temperature measured in Kelvin scale. So statement is volume occupied by the gas is directly proportional to absolute temperature is written as capital T. So this temperature must be measured in terms of Kelvin scale. A constant pressure and the constant amount of gas. So this is the statement of Charles law. So Charles law, pressure and constant, volume occupied by the gas is directly proportional to absolute temperature. So these can be written in different forms. Look at this. V is equal to some constant K into T. Let it be equation 1. So this can also be written as, look at this, volume divided by temperature. The ratio of volume to that of temperature is always a constant. If this is constant, then we can say V1 by T1 is always equals to V2 by T2, which is always a constant. So this ratio remaining constant provided pressure and number of moles remain constant. The equation can also be explained in terms of graphical form. So we take the graph here. Logarithm. So logarithm of volume is equals to logarithm of K plus logarithm of T. Let this be equation 4. The same can also be expressed in this way. So logarithm of V is equals to logarithm of K plus or minus logarithm of 1 by T. Log 1 is 0, so log A by B means log minus T, so minus minus comes out to be positive. So these are different forms which represent same law, that is Charles law. Now we have to explain this in terms of graph. So the graphical representation. Graphical representation. So Charles law, pressure remaining constant, so we have pressure being constant. So a process in which pressure remaining constant is known as isobars. So the graphs representing Charles law are known as isobars, means the pressure remaining constant. So look at this equation 1. So we have volume versus temperature. So this is equation of straight line passing through origin. If the graph is for different pressure, then this looks like, suppose this is P1, P2, P3, P4. So volume versus temperature graph, equation 1, at different pressures. Moving from P1 to P4, pressure decreases. That means this is the graph at low pressure, this is the graph at high pressure. So P1 is greater than P2, greater than P3, which is greater than P4. So this represents equation 1. Now graph representing equation 2. So look at this. ratio of volume versus temperature. Ratio of volume versus temperature. So these volume versus temperature, volume by temperature ratio versus volume और 1 by T, अगर इसका ग्राफ बनाएंगे, then this always remains a constant, means this ratio is always a constant. So we have a graph which runs parallel to x-axis, but at different pressures will have this, that is P1, P2, P3, P4. So moving from P1 to P4 pressure again decreases. So this represents equation 12, equation 3. Then we have this graph representing equation number 4. So we have graph of logarithm of volume versus logarithm of T. So if you look at this graph, the slope is +1, so they have an increasing slope. Extrapolation, this point is equals to log k, that is y-intercept, and the slope is +1, that is equation 4. And finally equation 5, log v versus log 1 by t. Log v versus log 1 by t. Again, if you look at this, slope is -1, so we have a decreasing slope. Extrapolation, this y-intercept, this is equals to log k, and this slope is equals to -1. So this is Charles' law. So Charles' law, pressure constant, n constant, graph is known as isobars, same equation in different forms, and this is the graphical representation. Then the third gas law that we are going to discuss is Gay-Lussac's law. Gay-Lussac's law. Now this Gay-Lussac's law, or before this Gay-Lussac's law, I'll give you one more statement of this Charles' law. Now if suppose the Charles' law is to be explained or stated in terms of degree centigrade, temperature measured in terms of degree centigrade, then this Charles' law is given as volume occupied by the gas at T degree centigrade is equals to volume occupied by the gas at 0 degree centigrade, which is known as V naught, plus V naught by 273.15 times T degree centigrade. So this is the Charles' law in terms of degree centigrade. So V naught is the volume occupied by the gas at 0 degree centigrade. This is the volume occupied by the gas at 0 degree centigrade. Now look at the difference between the two. If the gas temperature is measured in terms of degree centigrade, so at 0 degree centigrade, this gas has got certain volume. So at 0 degree centigrade, gases do have certain volume. The volume occupied by the gas at 0 degree centigrade is some finite value. But if we look at the statement of Charles law in terms of Kelvin scale, volume occupied by the gas at 0 Kelvin is always 0, because V is equals to kT, temperature Kelvin. If temperature Kelvin is 0, then volume occupied by the gas is 0, so both are same. So I say volume occupied by the gas at 0 Kelvin is always 0. Volume occupied by the gas at 0 degree centigrade will be some finite value, that is known as V naught. So these two equations, this equation and the another form, both are identical. So look at this. For every gas, if temperature increased by 1 unit, then the volume occupied by the gas increased by a factor of V naught by 273.15. So every change of 1 unit temperature, the volume occupied by the gas changes by a factor of 1 by 273.5 times the volume occupied by the gas at 0 degree centigrade. So this is another statement of Charles law in terms of degree centigrade. So look at this. Let this be equation number 6. So look at this. Take this LCM. So we have 273.15. So V naught 273.15 and plus T degree centigrade. So now look at it. This is V naught by 273.15. This temperature, that is T degree centigrade plus 273.15. So look at it. This is a constant. V naught is always a constant. This is also constant. So this is K. This temperature, degree centigrade plus 273.15, this is defined as Kelvin temperature. So the Kelvin temperature is T plus 273.15. So though the equation was developed by Charles, but Kelvin, another scientist, says this could be another unit of temperature, which, so in honor of this Kelvin, this temperature was known as Kelvin temperature. Now look at this. खोजा किसने? चार्ल्स ने. क्रेडिट किसको मिला? केल्विन को. So if it means both the equations are same, so volume occupied by the gas at absolute temperature, both are directly proportional. So at 0 degree centigrade, volume is 0. At 0 Kelvin, volume is 0. At 0 degree centigrade, volume is some finite value. So look at this equation number 6 graph. So this is volume, this is temperature, 0 plus minus degree centigrade. At 0 degree centigrade, volume occupied by the gas is some finite value, that is V naught. If temperature increases. If temperature decreases, V naught minus this, so this factor decreases. So this point is minus 273.15 degrees centigrade. So if you look at this, when we decrease the temperature beyond 0 के नीचे, the volume occupied by the gas decreases and finally this reaches 0 volume. So यहाँ पे volume of gas is 0. तो यहाँ पे volume of gas 0. Is it possible कि आपके पास एक substance है जिसका certain volumes है, अब temperature decrease करते गया, volume gap हुआ. अगर volume gap हुआ तो substance gap हुआ. भाई, is it possible? Not possible. So if we have a substance do have some volume because we have a gas. Even at 0 we have some volume of gas. तो 0 से temperature कम करने से ये gap हो गया. तो this signifies that at this particular point the physical state changes. All this gas has been converted into liquid. The physical state means gas disappears and this changes to another state, that is this liquid state. That means even before reaching this particular point, the volume of gas which changes to this particular point, before this point the gas will be liquefied and gas is converted into liquid. So this means any given gas, the minimum temperature up to which a gas can be cooled is minus 273.15. So according to Charles, the minimum temperature up to which a gas can be cooled is minus 273.15 degrees centigrade. And this, beyond this point, the physical state, or even at this point or near this point, the physical state of gas disappears and this appears in the form of liquid. The physical state changes. So gas will be, before this temperature, gas will exist. At this temperature or beyond this temperature, gas will disappear and this is converted into liquid state. So again I am repeating the sentence. According to this Charles law, the minimum temperature up to which the gas can be liquefied is cooled is minus 273.15. 8 or near this point gas disappears and volume changes to 0. So this is Charles law in degrees centigrade. So after this Charles law, we will go to Gaseous law. Gaseous law. Now for this Gaseous law, condition is volume has to remain constant. So volume should be kept constant and number of moles or amount of gas should be remaining constant. Volume and the quantity of the gas has to be kept constant. Under this condition, the pressure exerted by the gas is directly proportional to absolute temperature, means temperature measured in Kelvin scale. So the statement can be written as P is equals to some constant K into T, let this be equation 1, or can be modified as P by T, ratio of pressure to that of temperature is always a constant, or we can say P1 by T1 is equals to P2 by T2. This is always a constant. So equation 2. If you look at it, this is exactly parallel to Charles law. The only difference is यहाँ पे pressure था, वहाँ पे क्या था, volume था. Similarly, we can have look at this. Log P is equals to log K plus log T, equation 3. Log P is equals to log K plus minus log 1 by T, equation 4. Then if the measurement is in terms of degree centigrade, equation is pressure exerted by the gas at T degree centigrade is equals to pressure exerted by the gas at 0 degree centigrade plus P naught by 273.15 times degree centigrade. That means for every change in temperature by 1 degree, pressure changes by a factor of 1 by 273.15 times pressure exerted by the gas at 0 degree centigrade. So this is equation number 5. These equations and the forms are exactly parallel to Charles laws. The only difference is wherever we have volume in case of Charles law, that volume should be replaced by pressure P. Graphs, everything remaining identical. Graph. Since we have volume constant, so volume constant, process in which volume remaining constant is known as isochore. So the graphs representing Gay-Lussac's law are known as isochore, means volume constant. So I'm just drawing the graph. All the graphs are exactly parallel to that of Charles law. Take this pressure, temperature. So pressure, temperature. So pressure is directly proportional to temperature. So equation of straight line passing through origin. So this is V1, V2, V3, V4. So moving from V1 to V4, volume decreases. So V1 is higher volume, this is gas at low volume. So this is equation 1. Now equation 2, P by T is always a constant. So we have ratio of P by T versus P or 1 by T graph. This is always a constant. At different values of V, we have these graphs V1, V2, V3, V4. So V1 to V4, again volume decreases. So this represents equation 2. Equation 3, log P versus log T. Equation of straight line with slope plus 1. So we have this equation. Positive slope, extrapolation, y-intercept, log K, slope plus 1. That is equation 3. Now equation 4 and equation 5. Log P versus log 1 by T. So the slope is -1. Extrapolation, y-intercept is log K, slope -1. Equation 4. And finally equation 5. This is P, T0, this is positive, this is negative. It is Pt. At 0 degree centigrade, pressure is P naught. At 0 Kelvin, pressure is 0. This is minus 273.15 degree centigrade. This is P naught. The slope is P naught by 273.15. So this represents equation 5. So these are Gay-Lussac law, its graphical representation. So Gay-Lussac law and Charge law equations are parallel and graphs is also almost parallel to each other. The only difference is in one case we have pressure and the other case we have volume occupied by the gas. Next gas law, experimental gas law, is Avogadro's law. Avogadro's law. So Avogadro's law, for this Avogadro's law, pressure of the gas should remain constant as well as temperature of the gas has to remain constant. So at constant temperature and pressure, the volume occupied by the gas is directly proportional to the number of moles. So volume occupied by the gas is directly proportional to number of moles at constant temperature and constant pressure. If volume is also constant, then the number of moles or number of molecules of gas will always be a constant. So we have this. So therefore look at this. V is equals to some constant K into number of moles. So number of moles and volume is directly proportional to each other. Means if the number of moles is increased, volume of the gas will increase. If the number of moles decreases, volume occupied by the gas will also increase. So therefore look at this. Let us see equation 1. Now this can be written as volume is equal to some constant K. Number of moles is mass of the gas divided by molar mass. This is mass, this is molar mass. So therefore look at this. Molar mass is equals to K into mass divided by volume. Or we can say molar mass is equals to K into mass by volume is density. This D is equals to density. So this equation says molar mass of a gas is directly proportional to the density of the gas. So that is molar mass of the gas is always directly proportional to the density of the gas provided pressure and temperature remaining constant. So at a given pressure and temperature, the molar mass of the gas is directly proportional to density. This is also known as Avogadro's law, or simply we can say the most common statement that we often find in the books is at given pressure and temperature, volume occupied by the gas is directly proportional to the number of moles or the number of molecules. So mole is the number of molecule, more will the volume occupied. Less is the number of molecules, the volume occupied by the gas molecule will be less. So the derived equation is molecular mass of the gas at a given temperature and pressure is always proportional to the density of the gas. So if you make the graph mass versus density, then this will make a graph straight line passing through origin. So look at this. We have this volume versus n. So equation of straight line passing through origin. And for the slope is equals to K. If you make this graph, molecular mass versus density, Then also we have a straight line passing through origin. Again we have a slope is constant k. But if we made a graph between volume and mass, this is a mass of gas, this is a volume of gas, we have to look at this. Again, this is equation of straight line passing through origin. The only difference is slope will change, so slope is equals to k by molar mass. Or if we made a graph between volume versus 1 by molecular mass, again this is equation of straight line passing through origin, but the slope will change and the slope becomes k into mass of gas. So this is Avogadro's law. So these four gas laws, that is Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, these explains the experimental gas laws which is experimentally observed. Why this is so? We have to develop a theory, and that we will take up in the next video lecture. Hopefully you enjoy this introduction of gaseous state.